Hello, class. Welcome to Lecture 17. We're going to continue our much more nuanced discussion of phase transitions today, considering both those concepts we introduced last lecture of universality and symmetry, and how we can use those to motivate simple models that makes the consideration of phase transitions a little more tractable than they would be otherwise. So as usual, let's begin by reconsidering some of the things that we hit upon last lecture, reminding ourselves of a couple of really important facts about the phenomenology of phase transitions before we get into introducing a couple simple models and trying to make some sense out of them. So one of the most important features of a phase transition, a thing that really defines a phase transition mathematically, is the existence of a non-analytic change in the free energy. Specifically, we would say that phase transitions are marked, are delineated, are defined by a non-analytic change. To the free energy. To have such a non-analytic change to the free energy requires a couple of non-trivial statements to be made about the underlying microscopic degrees of freedom in order to endow those microscopic degrees of freedom the ability to generate a non-analytic change. In fact, we saw last time that the structure of the partition function with which for which the free energy is equal to, up to a log and a constant factor of kBt, in order for that partition function to have a singularity in it, because that partition function is a sum of smooth functions, there must be an infinite number of terms in that sum. And not only that, so not only do we require a thermodynamic limit, but that the system can't be broken up into non-interacting parts. So it's a non-trivial thermodynamic limit in which a infinitely large system with infinitely long-range correlations exists. So to have that non-analytic change, that singular point in the partition function requires correlations that span macroscopic scales. Otherwise, we could partition our system into individual boxes, each of finite extent. If those were non-interacting, then the partition function would be a simple product of those terms, which while super extensive, the free energy being extensive in those variables by taking the log would not give rise to a infinite singular response. Long-range correlations, however, by themselves are not sufficient. We have to take both the length of correlations to be large and the size of the system to be large as well. That's the only way we can get something singular, something sharp, something non-analytic to happen in our partition function, which is otherwise a sum of smooth functions. This is a little bit abstract. We can make it concrete by citing some examples. So for example, if we were considering a liquid vapor transition, what we really mean by a singular or non-analytic response is noted by considering what happens if I measure the volume of a gas as a function of the pressure, and note that there is a point, a coexistence point, by which if I take that vapor and I begin to press on it by applying a pressure, I will undergo a sharp transition, a condensation transition in this case, where that vapor spontaneously changes into the liquid. And the breadth of that transition is infinitely sharp in the sense that there's a finite change in the volume over an infinitesimally small range of pressures. This could be uncovered by considering the compressibility, which is nothing but that derivative dv dp up to a minus sign and a factor of volume to make it intensive. If we were to measure the compressibility of the system as a function of pressure, at that coexistence pressure, the compressibility is infinitely large. Indeed, we uncovered last lecture that the compressibility being proportional to the fluctuations in the volume implies that the scale of fluctuations becomes infinitely large. That too can only happen if all particles are correlated with all other particles, that there is macroscopically long correlation lengths such that there is no truncation in the correlation when I compute the or there's no truncation in the double sum that emerges when I compute the variance of the volume fluctuations. So I think this is hopefully becoming clearer, and it does in principle present a bit of a problem because studying systems with correlations is difficult. Because our trick, the way in which we've actually computed partition functions, made contact between molecular and macroscopic observables, has required this factorization of the partition function, which doesn't happen if the system is interacting, a requirement for there to be correlations. I can rewrite that a little bit clearer. But as we noted at the end of last lecture, there is some hope. There are some simplifications that phase transitions offer. And that comes from the notions of universality and of symmetry. In fact, the requirement of long-range correlations and the emergence of universality are not unrelated phenomena. The fact that molecules become correlated over very large length scales means that average properties are not dominated by small length scale features. The average is not given by what an individual particle is doing anymore, but rather what a collection of particles are doing. That average then knows much less about an individual molecule. And so those molecular details play a much smaller role in phase transition behaviors because those correlations average over a lot of those molecular details. And we've noted some specific examples of universality. in the context of second order phase transitions, where the second derivative of the free energy is singular, by considering a few examples like liquid vapor transitions, like miscibility transitions, and magnetization transitions, each of which has an order parameter that distinguishes those two phases. In the liquid vapor transition, a distinguishing feature between a liquid and its vapor is just the density. Indeed, if I was to plot the density of the liquid in coexistence with the density of its vapor, I would find, as a function of temperature, a plot that looks like this. If I set the system up with a density within this region, so for a temperature and pressure that puts it in there, I would find the system at coexistence. What that would mean is that I'd get some amount of liquid and an interface separating it from some amount of vapor. However, if I made the system higher density such that it was over here, I'd see only a pure liquid, or over here, only a pure vapor. That distinction between liquid and vapor ends at a critical point with an associated critical temperature and critical density. If rather I thought about a miscibility transition, say between oil and water demixing, we know that at low temperature, if I set up a solution of oil and water, it would phase separate. That does not mean that each phase is pure, rather that it's the majority of, say, the oily phase is oil with some sparingly soluble amount of water in it. And analogously, the water will have some oil in it. The amount of oil soluble in water will increase as I increase the temperature. And at a particular temperature, its critical temperature associated with a critical composition, that coexistence region will cease being distinguishable, and I will be able to make mixtures of oil and water soluble in all compositions. So in this case, in a miscibility transition, the order parameter distinguishing one phase, say the oily phase, from another, the watery phase, is just the mole fraction of one component in the other. Sorry about that. Finally, and a little more abstractly, one could imagine taking a magnet, which will have some net magnetization, which could be either up or down. If I increase the temperature, that magnetization will get smaller and eventually go away. The location in terms of temperature where that magnetization, that magnetic moment of the bar magnet I'm holding in my hands, that the temperature at which it goes away is its own critical temperature. Indeed, I can, in principle, put two magnets in coexistence with each other, and they would form a domain where all the spins align in one direction, and a domain where all the spins point in another direction. That would be an example of coexistence in a magnet or magnetic system. That coexistence goes away at that critical point and at zero magnetization. So here are three very distinct seeming transitions: liquid vapor transitions, mixtures, miscibility transitions, and magnetization transitions. And yet, while they are very different molecularly, they all behave quantitatively similarly. In fact, if we were to measure near the critical temperature the behavior of each of these systems, say independent of what liquid vapor transition I was considering, if I measured the density of that fluid less that its critical density as a function of temperature less that its critical temperature, I would find, independent of the molecule of interest, that density goes to the critical density as a power law with a exponent of 0.32. Similarly, if I measured how the composition changes relative to the critical composition as a function of temperature for a host of different mixtures, I would find the same power law, scales like the temperature to the 0.32 power. And finally, the absolute magnitude of the magnetization, which goes to 0 at the critical temperature, does so with the exact same power law, 0.32. That power law we give, or that exponent we give a symbol to, we call it beta, and it is known as a critical exponent. It manifests quantitatively the universality through which these seemingly disparate transitions all seem to agree. So even though they're made out of different components, the two phases seem very different in their physical and chemical properties. There must be some sense in which they all are the same sort of transition lurking underneath. There must be some commonality associated with this transition, which generates universal, independent of molecular detail behaviors. So while we are confronted with the fact that in order to study phase transitions from a statistical mechanics perspective requires us to study interacting systems, which is hard, there's some notion by which we can envision studying one of these cases in detail and learning quite a lot about all of the others. In fact, in doing so, we might uncover how it is exactly that these transitions all relate to each other. Now, if there were only one critical exponent, maybe you would think that this is maybe not the best use of your time, but in fact, associated with these three transitions are a whole host of different critical exponents. For example, if I was to measure the heat capacity of any of these systems as a function of temperature, as I neared the critical temperature, they would all find a diverging heat capacity with a particular form of the divergence, which scales like a power law for temperature relative to its critical temperature, with an exponent, usually denoted alpha, where for all of these three transitions, liquid vapor, magnetization, and demixing, that alpha, that critical exponent, is 0.11, pretty low power. It's a pretty weak divergence, but a divergence nevertheless. And similarly, for the so-called generalized susceptibility, which for the liquid vapor transition is just its compressibility, Analogously, if I was to measure it as a function of temperature near its critical temperature, I would find a divergence with a particular power law. Here, a critical exponent is introduced, often denoted gamma, where that gamma for liquid vapor, magnetization, or miscibility are all 1.2. So that susceptibility which is how the order parameter changes with an applied conjugate field, it diverges in a particularly universal way. All right, so that's the concept of universality. It's going to simplify our life by exposing common structure between seemingly disparate transitions. The other important concept in the statistical mechanics of phase transitions is the notion of symmetry. To concretely discuss symmetry, let's consider our magnet. For which the symmetry is, I think, the clearest. If I took a bar magnet, one with a permanent molecular or magnetic dipole, say in the z direction, some finite positive number, as we discussed last lecture, if I was to heat this magnet up, if I tossed it in the microwave, I could demagnetize it. I would need to heat it to some temperature above its critical temperature. And if I did that, I would still have a bar magnet, imagining I don't heat it up so high as to melt it. But if I was to measure its magnetic moment, it would be 0. However, if I cooled it back down, we expect that I could do so slowly. If thermodynamics works, I would expect to be able to retrace my steps, find a reversible path by which I can go in the forward direction and backwards in the backwards direction and back to the backwards direction, regenerating a net magnetization. And while it is true that if I were to cool it back below Tc, I would spontaneously generate a magnetic moment. However, only 50% of the time would I find that the magnetic moment points in the same way that it did originally, with an mz greater than 0. 50% of the time, I would find a magnet pointing in the opposite direction, with an mz of the same magnitude, but negative in sign. That is to say that from the individual spin perspective, microscopically, spins don't really care about this arbitrary direction I've labeled as z. In fact, if I was to look at two configurations of 6 spins, say something like this, or the same configuration only rotated such that all the spins are flipped. If I flip all spins simultaneously, that is just like relabeling my axis. The spin shouldn't care about that. Energetically, the system should have the same, the system should feel the same energetically, one way or the other. If they have the same energies, they necessarily have the same Boltzmann weights. Which leaves us with a bit of a paradox, because how is it then that the magnet can regenerate a permanent moment? And why is it that it does so by 50% of the time splitting into a magnet that points up and 50% of the time splitting into a magnet that points down? The resolution to this is that while it is the case that this 50-50% of the time I'm up or down preserves that symmetry, that's a macroscopic symmetry that's not broken. Microscopically, that symmetry is spontaneously broken. In fact, we can think about what that would look like if I was to plot the Helmholtz free energy as a function of magnetization. The up-down symmetry, the independence of how I've decided to label the z direction, must mean that the system has an equal free energy for pointing up or pointing down. However, there's nothing to preclude the system from having two degenerate basins with a barrier separating those up and down directions. So from a Boltzmann perspective, there's still equal weights, equal probability of being up or down. However, because the probability is just proportional to the Helmholtz free energy. However, it must be the case for a individual magnet to have a permanent magnetic moment macroscopically. It must be the case that once the system has decided spontaneously whether to be up or down, it is impossible to change direction. That must mean that the barrier for changing up to down or vice versa must become prohibitively large as the system gets large. And indeed, the barrier height goes to infinity as the scale of the system goes to infinity. So above TC, there's only one could imagine that there's only one minima, that associated with zero magnetization. So on average, indeed, up-down symmetry is preserved microscopically as well as macroscopically. However, if I cool the system back down, an individual magnet can decide whether or not it's going to fall into the down basin or up basin. And once it's done so, a macroscopic magnet will never change that sign spontaneously. A complementary way of thinking about this is to consider the other experiment we discussed last lecture, which is what happens if I stay below TC, but apply a magnetic field. So one could imagine doing an experiment whereby the magnetic moment is measured as a function of some applied field. Let's denote that H as an external field. If T is less than Tc, exactly at zero applied field, if I look at an ensemble of magnets, the magnetization must be zero. However, it can be zero because half of the time I have a magnet with a positive magnetic moment, and half the time I have a magnet with a negative magnetic moment. If I apply a field, I will necessarily break that symmetry, increasing the magnetic moment to something positive. Or if I apply a field in the opposite direction, I can drive that magnetization in the opposite way. This implies that a very small field breaks the symmetry. An infinitesimal field breaks the symmetry, favoring one net magnetization over another. So indeed, put together, the notions of symmetry and universality then motivate us to try to construct really minimal models that have only the necessary amount of molecular detail in order to try to interrogate and make some sense of the phase behavior that can emerge from such ingredients. Okay, so that's what the rest of this lecture is going to be about. Introducing two models that we'll consider in a significant amount of detail in subsequent lectures. And we'll do this within the context that we've been working thus far, in the context of magnets and liquid vapor transitions. So the first model we'll introduce is for a magnet and was invented by a graduate student named Ising, and is now carries his name and is known as the Ising model, or Ising's model. Okay, so as anticipated, this model is really a bare bones model of what a magnet might be. So a magnet, you typically think about spins in a solid. So indeed, let's imagine, that we have some lattice. I will draw this in 2 dimensions, but could exist in 3 dimensions. Like so, where these extend further into space. And at each one of the intersections on this, say, square lattice, sit a spin that could be pointed in the up or down direction. Like so. So that is a spin. At some lattice site, call it site I, and we'll have some local moment associated with that spin. Let's say that that moment is plus or minus mu sub I. That means that mu sub I, let's for simplicity, imagine that mu sub I, whether it's up or down, has a fixed magnitude, call it mu naught, and let's associate it with then a binary variable, s sub I, that is plus or minus 1. Okay, so those then define our dynamical degrees of freedom, the spins sitting on a lattice site. Now, what do we know about spins? Well, spins tend to align with external magnetic fields. We've already introduced notation for an external magnetic field. Call that capital H. So that the energy associated with those spins is going to be favorable for a field pointing in the same direction. So if H points along the z-axis, it's going to couple to each one of those spins who has magnitude mu naught and acts conjugate to the total magnetic moment, which is then just the sum over all of the spins. Let's say there are n of them. So that's a single spin Hamiltonian. It tells you that a tagged spin likes to align in a field of magnitude capital H. But we know that the spins residing on a lattice will, in addition, interact with each other. Now, the simplest possible interaction, the first order interaction, we can imagine putting into this model is a so-called exchange interaction. There's an exchange coupling, a coupling resulting from the overlap of those spin wave functions acting on each site. That will be favorable, so that J is some positive number, minus J then telling you that the energy is lowered if spin I and spin J are pointed in the same direction. So if I equals Sj, that would return a plus 1. That would be Si squared, which is plus or minus 1 squared is plus 1. So indeed, if the spins are in the same direction, if it's plus 1, if both are plus 1 or both are minus 1, that will be favorable. Otherwise, it's minus 1 if Si is not equal to Sj. 1 times minus 1 is minus 1. That would be an unfavorable or repulsive interaction. Now, those exchange interactions are fairly local in space. They arise from dipole, spin dipole, magnetic dipole couplings and die off fairly quickly. So it's a reasonable approximation, and as Ising made, to consider spin-spin interactions as only those associated with the nearest neighbors of an individual spin. So what I mean by that, I'll denote it by a prime. And will mean that this spin, for example, only interacts with the neighbor to its right, the neighbor above it, neighbor to its left, and the neighbor not shown down below on a square lattice. So there would be 4 nearest neighbors on a square lattice, 6 on a cubic lattice, etc. And again, just to sum, those spins align with each other, and we call that an exchange energy. All right, and that's it. We'll assume that it is sufficient to consider only the lowest order interaction and only the shortest, the largest interaction between the spins. So only spin-spin interactions, so one spin times another spin, and only those in the nearest neighbors of an individual tag spin. And that's Eisen's model. So there's a field component, which for simplicity, we can go ahead and just roll these 2 variables, capital H and mu naught, into one, call it a little h. And so Eisen's model consists of 2 terms: an applied external field, whose magnitude is h, acting on individual spin variables, si, and a spin-spin interaction with strength j, denoting the exchange interaction strength. So for Eisen's model, the total partition function could be written down by noting that the microstate of the system is just the set of spin variables, all the si's, in the canonical ensemble where the volume, thus the number of lattice sites, is fixed, the number of spins is fixed, and the temperature is fixed. So that's the canonical partition function Q, can be written as a sum over all of those spin variables. We'll denote this shorthand curly brackets S as a sum over S1, S2, all the way up to Sn. The Boltzmann factor associated with that microstate is e to the beta, a sum, let's call it beta j, a sum over nearest neighbors, again denoted with that prime, si, sj, plus beta little h for the applied magnetic moment or magnetic field, sum over si. And so that is the partition function. And as we anticipated, it's not simple to solve because it doesn't factorize. There's no simple way of pulling out all of the terms that have to do with si and not some sj. That's kind of a bummer, but a bummer we expected. It is worthwhile to note that, as we expected from our discussion on symmetry, that if little h is equal to 0, the model does have an up-down symmetry. If 2 spins are pointed in the same direction, it doesn't matter if they're both up or if I flip them all so they're both down. And similarly, if they're pointed in opposite directions, if I flip all the spins again, that again retains the same value. So the beta j sum over products of two spins, if I flip all the spins, is left invariant. So the weight of a system, a configuration in the absence of an applied field, retains this up-down symmetry. If I have a symmetry operation where I flip all the spins simultaneously, it returns back the exact same Boltzmann factor as the system before that operation was acted upon it. Okay, so for the moment, let's leave it there. So that's our Ising model partition function. Now let's introduce another model, one for a liquid vapor transition. This one does not have a single name associated with it. We call it generically a lattice gas. This case, one with explicit interactions. So as we've done before, we can imagine taking a part of a system, gridding it up into space, like so, where in each one of these volumes, there could be particles, in which case I could imagine the density is such that it's associated with a liquid density. Otherwise, there could be no particles, in which case that is indistinguishable from a vacuum or from a vapor. So let's denote a cell that is filled with a liquid-like density. Let's denote that with an indicator function Ni that equals 1. To be contrasted with a cell that is empty or has a vapor-like density, that has an indicator function, say for that jth cell, that's 0. So that each cell has an indicator function which is either 0 or 1. All right, so those are our dynamic variables. It's just whether or not particles are someplace in space. If I'm on a small scale, there's not really a meaningful distinguishing density between a vacuum and a vapor. For all intents and purposes, a vapor has the same sort of density as a vacuum, very small relative to the liquid. So those are the dynamic variables. What about the energetics? Well, I would expect that two cells that are both liquid-like, that have particles there, should have some favorable interaction. Let's associate that interaction with a single number, epsilon. So those could be, for concreteness, the van der Waals interactions between liquids in one of those cells and the liquid or particles in the other cell, the adjoining cell. Now, if one of those cells is in contact with a vapor, we essentially are envisioning that there are next to no particles, so there would be no interactions there. So an energy function follows, which is that for each pair of cells that are both filled, I get a minus epsilon of attractive energy. One way to ensure that that is only the case if both cells are filled is to have a product of Ni and Nj. Only if both of those return 1 do I get that favorable interaction. If either of those cells, I or J, are empty, there's nothing to interact with, I'll get 0 energy back. And for simplicity, let's imagine that these two interactions are sufficiently short-ranged on the scale of the grid we've put down, such that only nearest neighbor interactions need to be accounted for. And we'll use that same notation of a prime on the sum to sum over I and j that are only nearest neighbors. Again, for concreteness, this product of Ni and j is either 1 if Ni equals Nj equals 1, and it's 0 else. So indeed, I only get a favorable interaction if and only if the two particles or the two cells are occupied. Now, if a cell changes from occupied to unoccupied, so as the n variables fluctuate, unless I constrain the total sum over n to be constant, that means that the number of particles are changing. And so it will behoove us to not consider this system in the canonical ensemble, but rather in a grand canonical ensemble, where we don't have to worry about the constraint that the total number of filled cells is constant. For the grand canonical ensemble, we need both an energy function and a way of knowing how many particles there are in the system, but that's easy. There's a one-to-one mapping with the total particle number and the number of filled cells. All right, so just as before, we can write down the partition function for the system. The microstate now is defined as all the occupation numbers. So those are what I need to sum over. So the N1 being 0 or 1, N2 being 0 or 1, all the way to Nm if I have M cells. And now as a grand canonical ensemble, I have an energetic contribution, gives me a beta epsilon restricted sum over I and j and I and j, plus a beta mu sum over Ni for the total number of particles in the system. All right. So that's the grand canonical partition function for the lattice gas. if you were to scroll up and compare that to the partition function for the Ising model, the model of a simple magnet, apart from the labels we've used, those partition functions look very similar. So Q, the form of Q Ising, and that for the lattice gas look very similar. In fact, we could write them in the exact same way through a transformation where instead of summing over binary variables that are 0 or 1, we change them to the spin variables, which are plus or minus 1. So Q Ising has microstates defined with the spins, which are plus or minus 1. The lattice gas has binary variables, which are 0 or 1. If Si was equal to twice Ni minus 1, that would be a unique mapping that sets for all empty cells a spin value of minus 1 and all filled cells a spin value of plus 1. If we make that mapping, if we redefine the spin variables as those binary variables, we could then take a sum over all the spins, which is in the Ising model partition function, multiplied by the applied magnetic field. That would be the same as twice a sum over binary occupation variables minus however many lattice sites there are in the lattice, in the Ising model. And analogously, if we took the exchange interaction in the Ising model with that restricted sum over products of spins and rewrote it in terms of binary variables, the occupation variables of the lattice gas, we would get a factor of 4 times a restricted sum Ni in J from the first term in this transformation. We'd get a minus 4 times a restricted sum over just Ni, which is nothing more than 4 times whatever the coordination number of that lattice is by 2. Call that coordination number Z. And then just a sum over Ni. That's just saying that that sum has an index J, which is just summing over 1. I could do that sum and call that sum Z over 2. And finally, a term from the constant minus 1 piece in this transformation, which gives me 1/2 in Z as the total number of neighbors on a square lattice, or on a generalized square lattice, or a general lattice. So putting those together, the Ising energy function, which is minus the exchange energy sum over Si Sj restricted minus H sum over Si total magnetization, can be rewritten in the lattice gas variables as minus 4J sum over Ni in J restricted minus 2H plus 2JZ sum over Ni plus a constant. So if we associated this factor of 4J with epsilon, and this factor of 2H plus 2JZ as mu, we have indeed found that there is a mapping between the Ising model energy, written in terms of spin variables, and the lattice gas factor in the Boltzmann distribution in the grand canonical ensemble up to an additive constant really saying that these are exactly the same models, just rewritten in different variables. More strongly, that Q Ising, the partition function for the Ising model, is up to that constant, the partition function for the lattice gas. So in fact, studying one, the Ising model, for example, is has an exact mapping to the study of the other model, the lattice gas. The partition functions are the same up to a constant, which means that expectation values are exactly the same. So this is starting to give us some hints as to universality. If we write down two simple models for seemingly disparate transitions, a simple model of a magnet and a simple model capable of describing liquid vapor transitions, we found that those two models, while motivated in very different ways through physical arguments, nevertheless are mappable exactly to each other. In fact, we noted previously that the Ising model of a magnet has a up-down or Z2 symmetry. It must be then the case that the lattice gas similarly has that symmetry. At what is effectively H equals 0. At H equals 0, our mapping says that mu is equal to twice Jz. Yeah, sorry, there was a minus here. Right. Minus here, different in sign from this one. So along the Z2 symmetry line of the Ising model, the chemical potential in the Ising variables is minus twice jz, which is the same as minus epsilon z by 2, because epsilon and j are related through epsilon is 4 times j. So along that line, we should be able to demonstrate that the lattice gas similarly has an up-down or Z2 symmetry group associated with it. So let's see if we can actually write down that Boltzmann factor and illustrate that symmetry. So the Boltzmann factor, having both the portion due to the energy and the portion due to the fluctuating particle number, will have mu times the sum over Ni minus epsilon times the sum over Ni and j, restricted. Written in terms of the Ising variables, that's the same as along the symmetry line, epsilon jz by 2 with a plus, a sum over Ni, so along the expected symmetry line. And then our minus epsilon sum over Ni in j. All right, that's not obviously symmetric for SIs, all SIs going from -1 to +1, or the analogous mapping for the NIs. But there's a way to rewrite this first term. So sum over I, all the NIs, I could introduce a dummy variable, j, restricted, such now I sum over the neighbors of I. Well, then I'm going to overcount whatever is in the argument of that sum by a factor of z. So if I introduce that factor of z, that's just a very complicated way of adding 0. If I also note that Ni being 0 or 1 is the same as Ni squared, that means that I can square that without changing anything. Special trick of binary variables. So now I have two sums that are both over I and j, restricted to nearest neighbors, which means I can write them as one sum, epsilon out in front, a sum over I and j, restricted, Ni squared minus Ni in j, that's from the second sum. Now I and j, so the z's of course canceling from this z and that z. I guess I have undercounted by a factor of 2. Now, in this sum, I and j are treated in the exact same way. So if I have a function of just one of those indices, like Ni squared, it doesn't matter if I write that as Ni or Nj. So in fact, I can take only half from Ni if I add back half from Nj squared. That is then equal to epsilon by 2, pulling the 2 out. That'll give me, so if I did that here, those go away, that goes away, and I have a factor of 2 here. which is now manifestly a square. So if I have this restricted sum, I can now write that as Ni minus Nj quantity squared. So that is an exact rewriting along this special line where mu is equal to minus epsilon z by 2, which is the symmetry line that we found by first mapping to the Ising model and then noting that the Ising model has a symmetry about h is equal to 0. Now, is this a symmetric model? Well, if I goes to 1 minus Ni for all I, then the term in that sum, which is the whole term in the Boltzmann factor, the whole thing determining the weight of the configuration, Ni minus Nj quantity squared. So if I make the change, so if I swap all of the filled cells for empty cells and all of the empty cells for filled cells, it's 1 minus Ni minus 1 plus Nj, again, all quantity squared. The ones cancel, leaving me with Nj minus Ni squared, which, because the whole thing is squared, is the same as Ni minus Nj squared. So indeed, along this symmetry line, I can swap all the filled liquid-like cells for vapor-like cells, and I get the exact same statistics, the same statistical weight of that configuration. This is not an up-down symmetry in the same way that it was manifesting for the magnet. Rather, you would call this particle hole symmetry. Which is in the same Z2 group as the up-down symmetry of the Ising model. Just to drive this home, along this line of mu is equal to minus epsilon z by 2, which is our line of symmetry. If I took a configuration where I have that, this, and those cells filled, and I swapped all the filled cells for empty cells, and all the empty cells for filled cells, those two configurations along this line have the same weight. They contribute identically to any expectation value, and therefore it must be along that line that things like the critical point, if it exists in this model, must exist, where liquids are just as likely or just as probable as vapors. So a completely filled system would be identically as probable as a completely empty system. We don't, however, necessarily know that these simple models actually behave like we hope them to. We don't know that there is a phase transition in this model, that there are singular points in the thermodynamic limit. To do so, we would have to try to solve one of these models, and by correspondence, by equivalence, the other, in some way, and demonstrate that singular responses, that phase transitions exist. So can we solve, in some sense, the Ising model or the lattice gas? Well, typically what we have meant in this class by solving a model is to compute its partition function and thus have access to all of the expectation values that we might be interested in. For the Ising model, the probability of a configuration of spins, we've already noted, is this exponential of beta j, a sum over si sj, restricted to those nearest neighbors, plus beta h sum over si. If the j were 0 and it was a non-interacting model, we've solved that problem before. The fact that j is finite makes it seem like this model does not factorize. Indeed, if we were to try to write down the probability of a single spin being in a specific configuration, say P of S1, what's the probability that S1 is up or down? Gathering only those terms, for S1, we would have beta J S1 times the J's that are neighbors to S1 plus beta H S1. Indeed, therefore, the state of S1 depends on the states of some number of SJs. Which indeed makes our life hard. We can't close the calculation by just knowing what one spin is doing in a way that we could previously. Let's, for just this last little point of lecture today, try to simplify the calculation. What would happen if we considered this system in just one dimension? So one-dimensional chain of spins. So maybe that one, SI, is pointing up. Maybe this one, SI plus 1, is pointing down. Etc., like so. The energy for this one-dimensional set of spins is simple to write down. It's minus J times, now I can write the double sum over nearest neighbors as a single sum due to the geometry of a one-dimensional lattice as SI times SI plus 1. And at h equals 0, for example, that's all there would be. If I actually expanded out that sum, I would have minus J S1 times S2 plus S2 times S3 plus S3 times S4. And that sum would continue. Each of these products, however, an S1 times an S2, is either plus or minus 1. Either they're both the same, in which case I get a plus 1, or they're both different, in which case I get a minus 1. If we let SI times SI plus 1 be its own variable, BI, as in a degree of freedom that doesn't live on the nodes of this lattice, but rather on the links of them, which are plus or minus 1, it would seem that I could then write the energy as minus J sum over Bi. That looks like the energy is expressible as a sum over a seemingly independent variable. That makes it seem like, at least in one dimension, this problem will factorize, and we might actually be able to solve it. Well, I'll leave you in anticipation for what that solution might look like, and if we uncover some flaw in this argument, and what it would mean for the study of our phase transitions in the Ising model for the next lecture. So stay tuned for that, and I'll look forward to seeing you in the live session on Thursday. All right, everyone take care.